Imagine waking up one morning and finding out the entire planet has been cryogenically frozen. Not just your backyard. Everything. Oceans, continents, penguins, the works. This wasn't some seasonal cold snap. This was Earth's ultimate ice age on steroids, a global deep freeze scientists call Snowball Earth. Picture our blue marble transformed into a white cue ball, gleaming under the distant sun, locked in silence. No waves, no rain, no buzzing life. Just a planet pressing pause on everything. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, only if you enjoy these calm journeys through the universe. Now, let's begin. Now, to understand how bizarre that really is, we need to remember that Earth is not supposed to freeze over entirely. It's built with a pretty good climate control system. The planet has oceans that move heat around like nature's conveyor belt, volcanoes that keep the atmosphere stocked with greenhouse gases, and sunlight that keeps everything humming. For the entire planet to freeze, something had to go spectacularly wrong. And it did. But before we dive into the cosmic comedy of errors that turned Earth into a popsicle, let's set the stage. The story takes place roughly 700 million years ago, long before dinosaurs, forests, or even fish. The most advanced life on the planet could fit under your fingernail. Simple cells, algae, maybe a few colonies of early multicellular blobs doing their best impression of living jello. Earth was a relatively quiet place, geologically active, but biologically simple. And then came the freeze. Imagine standing on what used to be a tropical shoreline. Instead of waves lapping at your feet, there's solid ice stretching beyond the horizon. The ocean isn't a shimmering blue expanse anymore. It's a frozen desert of pale glass. The air is razor-sharp cold, thin and dry, the kind of chill that bites through skin and bone. Snow would crunch underfoot, but it wouldn't melt. Even the equator, the planet's warm belt, was smothered in glaciers. Earth had gone full refrigerator mode. Scientists think this deep freeze lasted tens of millions of years, long enough that entire generations of microscopic life would have come and gone without ever seeing liquid water. The idea that the entire planet could be frozen seems impossible, but geology keeps leaving behind these little breadcrumbs of evidence. Glacial rocks found near the equator, chemical traces in ancient sediments that whisper of ice and oxygen-starved oceans. It's like Earth accidentally left a diary of its worst winter ever. And now scientists are reading it one rock layer at a time. But let's pause on what that would feel like. The air would have been so dry and cold that snowstorms probably looked more like diamond dust drifting across the horizon. The oceans, frozen solid on the surface, might still have had a thin layer of liquid far below. Trapped heat from volcanic vents keeping small pockets of water alive. Above that, ice kilometers thick. The entire planet would have glowed a pale white from space, reflecting so much sunlight that it stayed cold even under the unblinking sun, and yet, while this was a frozen nightmare for most of the planet, it was also a strange kind of beauty. If you could fly over it, somehow surviving the cold, you'd see continents hidden beneath ice sheets, mountain ranges buried under glittering frost, and cracks where volcanic heat caused faint plumes of steam. Imagine auroras shimmering endlessly over a white world, the green lights dancing over an ocean that forgot how to move. So, how did this happen? That's a story for the next chapter. But for now, just think about what this meant for life. Everything alive back then had to survive without sunlight, warmth, or open water. Algae, bacteria, and early microbes were forced into the planet's few remaining safe zones: hot springs, volcanic cracks, or tiny unfrozen layers just beneath the ice. Earth was, in essence, an enormous snow globe, shaken by geological forces, where life clung desperately to any warm pocket it could find. What's remarkable is that Earth didn't stay this way forever. It came back. Somehow, through this deep planetary coma, life endured and the planet eventually thawed. But in that frozen silence, the seeds of future evolution were already waiting. This global freeze wasn't just a disaster, it was a reset button. It tested life to its limits, and when the thaw finally came, evolution was ready to explode in creativity. Snowball Earth was more than just an ice age. It was an era when our planet almost gave up, then reinvented itself. The frozen seas, the endless white deserts, the silent skies. These weren't the signs of death, but of transformation. Beneath all that ice, life refused to surrender. It endured, adapted, and waited, because even when Earth hit pause, the story wasn't over. It was just catching its breath before pressing play again. Billions of years ago, Earth wasn't supposed to look like a frozen marble. It was supposed to be warm and cozy, like a cosmic spa day. But volcanic gases, atmospheric chemistry, and a few unlucky coincidences threw our planet's thermostat out the window, leading to a feedback loop that turned oceans into glaciers. Basically, Earth pulled off the worst home temperature regulation failure in the history of the solar system. To appreciate the absurdity of this mistake, you have to picture early Earth's atmosphere as a delicate balancing act. Volcanoes were constantly belching out carbon dioxide and methane, gases that acted like an invisible blanket, trapping heat from the sun. Meanwhile, the oceans and rocks were like tidy housekeepers, absorbing and storing some of those gases to prevent overheating. Normally, this tug-of-war kept the temperature nice and stable. But at some point, things went sideways. One leading theory points to weathering, the slow, steady process where rainwater and carbon dioxide react with rocks to form minerals. When continents started shifting around and exposing new rock, this process went into overdrive. It was like giving the planet's atmosphere a massive carbon vacuum cleaner. Carbon dioxide levels started dropping, and as they did, the planet began to cool. The less carbon dioxide there was, the colder things got. The colder things got, the more ice formed. The more ice formed, the more sunlight was reflected away from Earth, making it even colder. And just like that, the planet's thermostat got stuck on deep freeze. This is what scientists call a runaway feedback loop, which sounds like something you'd hear at a bad rock concert but is much less fun. It's one of those natural systems that doesn't know when to stop. Once ice started spreading, it didn't politely pause at the poles. It marched across continents and oceans alike, reflecting sunlight like a cosmic mirror. What started as a chill breeze became a full-blown planetary lockdown. But this wasn't just about rocks and ice, it was about luck. Or maybe bad luck. During this period, the sun itself wasn't quite as bright as it is today. Early in its life, our sun shone about 6% dimmer, which doesn't sound like much until you realize that a small difference is enough to swing the climate from beach weather to planetary freezer. Combine that with the loss of greenhouse gases, and Earth found itself wearing an icy straitjacket. It's easy to imagine this as a slow process, but on a geological timescale, it was more like a sudden, unstoppable chain reaction. Oceans began to crystallize, turning once vibrant blue waters into a reflective shell. Mountains that had basked under warm rains found themselves cloaked in ice. Even the equator, normally a refuge of warmth, became a frozen wasteland. Earth had officially invented the ice cube look, and no amount of sunshine could melt it. If you could stand on the surface during this transformation, you'd witness one of the strangest makeovers in planetary history. The skies would have turned pale and thin, with sunlight scattering weakly through frost-laden air. The oceans would have started freezing from the surface down, trapping heat beneath layers of ice that grew thicker each year. There would be no rain, only fine snow drifting endlessly across continents. Rivers would have slowed to a crawl, eventually vanishing beneath the cold. And yet, deep beneath all that frozen silence, the planet was still alive. Volcanoes still rumbled. Tectonic plates still shifted, and the core still burned with molten heat. But all that internal fire couldn't compete with the icy fortress above. It's like trying to warm a refrigerator with a candle. Technically possible, but laughably inefficient. Here's where the story gets even stranger. While the surface froze, chemical reactions were still playing out under the ice. Oceans locked away dissolved carbon dioxide, making it impossible for the atmosphere to rebuild its warmth. The more the planet froze, the less chance it had to thaw. Earth had essentially locked itself inside its own snow globe, and no one was around to give it a good shake. This deep freeze wasn't part of some cosmic plan. It was the outcome of chance, chemistry, and timing. Earth didn't mean to become a frozen marble. It just stumbled into the wrong chain of events. If the continents had been in different places, or if volcanoes had belched a little more carbon dioxide, things might have gone differently. Instead, the perfect storm of cooling factors lined up like a planetary prank, and Earth found itself in the cold for millions of years. Now, you might be wondering, how cold are we talking? Scientists estimate average global temperatures could have plummeted below -50 degrees Celsius. For comparison, that's colder than Antarctica's harshest winter days. Even the air itself would have been brutal, thinner, drier, and likely filled with fine ice crystals. Standing outside, your breath would freeze before it hit the ground. Oceans became solid enough to support glaciers kilometers thick, slowly grinding across the continents beneath them. The most haunting part of all this is that Earth didn't even have anyone to complain about the weather yet. No mammals huddling for warmth, no birds migrating south, just microbes clinging to existence. The planet that would one day bloom with forests, its oceans, and life of all shapes and sizes had turned into a silent, reflective orb drifting through space. Yet in this catastrophic accident, something profound was set in motion. Earth's freezing wasn't just a fluke, it was a transformation waiting to happen. The same chemistry that had dragged the planet into ice would, much later, help bring it out again. But for now, the world was locked in its icy cocoon, cold, still, and glittering. A reminder that even the most stable planet can slip on its own frozen sidewalk. Earth didn't plan to look like a cosmic ice cube. It just hit an atmospheric banana peel and slid straight into deep freeze. Sometimes, even planets make mistakes, and this one would take millions of years to thaw out. Now, here's where the story takes an unexpected turn. We tend to think of continents as solid, unmoving things, but in reality, they're more like giant, slow-motion surfboards gliding over molten rock. During the era of Snowball Earth, these continental plates were engaged in a cosmic game of musical chairs, bumping into one another, breaking apart, and rearranging themselves in bizarre patterns. One particular supercontinent, called Rodinia, had begun to fracture and scatter its pieces across the globe. And when those pieces ended up near the equator, where sunlight was most direct, it set the stage for one of the strangest paradoxes in planetary history: the tropics that turned to ice. Here's the irony. The equator should have been the warmest place on Earth. Even with a faint sun, that central belt of the planet receives the most consistent sunlight. It's where you'd expect beaches, coral reefs, and tropical storms, not glaciers. But continental drift had unintentionally sabotaged the climate. You see, when land masses move, they change how oceans circulate. Those currents are nature's conveyor belts, moving heat from the equator toward the poles. When the continents cluster together or drift into awkward positions, those belts can jam, disrupting the planet's ability to spread warmth. During Snowball Earth, Rodinia's breakup created shallow seas around the equator, perfect for increasing the planet's reflectivity. Shallow water allows sunlight to bounce off more easily, and when ice began to creep in, it acted like a mirror, sending precious solar energy right back into space. It was a planetary feedback loop in motion. More reflection meant more cooling, and more cooling meant even more ice. Soon, those equatorial waters were no longer shimmering blue. They were white and silent. You can imagine the absurdity. Continents that should have been basking in eternal summer found themselves buried under ice sheets several kilometers thick. The sun rose every day, dutifully shining down, and yet the planet barely noticed. It's like trying to defrost your freezer by opening the door a crack. The cold just laughs at you. Geologists have actually found evidence of this frozen equator in rocks that were once laid down in tropical environments. The proof lies in glacial deposits, huge stones called drop stones that were carried by glaciers and dropped into fine ocean sediment as the ice melted. These have been found in places like Namibia, Australia, and Canada, regions that sat near the equator at the time, right? It's the geological equivalent of finding snow boots in a desert. The only logical explanation is that glaciers had reached right into the heart of the tropics. The movement of continents didn't just affect where the ice formed. It also influenced how the planet breathed. continental crusts are rich in minerals that absorb carbon dioxide from the air. When these continents sat in humid equatorial zones, rain and heat accelerated that weathering process, pulling even more carbon dioxide out of the atmosphere. The very placement of land near the equator was like a global air purifier that refused to turn off. With less carbon dioxide, greenhouse warming weakened, and the ice tightened its grip. This wasn't just a frozen postcard. It was an entirely new Earth. The once deep oceans turned into shallow, icy plains. The skies would have been a pale, washed-out blue, with sunlight reflecting so intensely off the surface that it could have been blinding. Day after day, ice crystals might have glittered in the atmosphere, scattering light into eerie halos. If you had stood on one of those equatorial continents, you'd see the horizon wrapped in white and the sky faintly glowing with reflected sunlight. A scene that looked more like an alien world than the one we call home. But the continents weren't done moving. Tectonic forces continued to push and pull them across the planet's frozen crust, sometimes causing volcanic rifts to form beneath the ice. Picture vast cracks opening up along the equator, belching steam and ash into an atmosphere already thin and cold. The contrast between fire and ice was extreme. Volcanic heat momentarily melting parts of the frozen seas before being swallowed again by the cold. The Earth was alive beneath its icy armor, flexing and groaning, as if trying to break free from its own frozen shell. It's tempting to imagine this as a static landscape, but even under a global freeze, Earth was anything but still. The continents shifted millimeter by millimeter, carving out the geography that would one day become familiar to us. Mountains were being born under glaciers. Valleys were being etched by ice sheets. In slow motion, the blueprint for future continents was taking shape, hidden beneath a planetary layer of frost. And there's something poetic about that. Even when locked in stasis, the planet was changing. Beneath the frozen equator, tectonic forces kept sculpting and reshaping the crust. The game of hide and seek never stopped. It just went silent for a while. The continents were still moving, still searching for their next configuration, setting the stage for a new Earth that would emerge once the ice receded. So, when we look at our warm, ocean-blue planet today, it's hard to imagine that once, the equator was a frozen wasteland. The very regions we now associate with sunburns and coconuts were once under sheets of ice thick enough to crush mountains. Earth's game of continental hide-and-seek had no winners, only lessons. It showed that even tiny shifts in where land and sea meet can change the fate of an entire world. In the end, those drifting continents didn't just move across the surface. They moved the story of life itself. By reshaping oceans and cooling the planet, they unwittingly forced evolution to adapt to extremes. The world would thaw eventually, but it would never be the same. The continents might have played a chaotic game, but their moves rewrote the script of Earth's history, turning the equator, of all places, into the coldest hiding spot of all. The atmosphere is supposed to be Earth's personal heater, a thin layer of gases that keeps warmth from leaking away into the cold vacuum of space. Without it, our planet would be as lifeless as the moon. But during the Snowball Earth period, that protective blanket all but vanished in its ability to hold heat. The problem wasn't that the air disappeared, it's that the mix changed. Carbon dioxide, the gas that does most of the heavy lifting in trapping warmth, fell to levels so low that Earth's climate system simply stopped working. To understand what went wrong, imagine the atmosphere as a sort of financial system for heat. The sun deposits energy, greenhouse gases invest it, and the planet spends it to stay warm. When carbon dioxide is plentiful, the system runs smoothly, just the right balance between savings and spending. But when too much carbon dioxide gets withdrawn, the economy of warmth collapses. That's exactly what happened. Weathering of rocks, ocean chemistry, and continental positioning all conspired to drain the planet's carbon bank, leaving the atmosphere bankrupt in thermal currency. The result was catastrophic. The thin film of gases around Earth began to lose its ability to trap infrared radiation, the heat the planet naturally emits back into space. Without that trap, warmth simply escaped. Days still brought sunlight, but the nights were long, dry, and deadly cold. Slowly, the entire thermal balance tipped. The atmosphere hadn't just cooled, it had ghosted the planet, vanishing in usefulness right when Earth needed it most. Scientists believe that carbon dioxide concentrations may have dropped to just a few hundred parts per million, or even lower, numbers that would make modern climate scientists' jaws drop for entirely different reasons. For comparison, today's atmosphere holds over 400 parts per million, and that's enough to make us sweat through global warming. But during Snowball Earth, the pendulum had swung in the opposite direction, turning our planet into a reflective freezer with no thermostat. Without greenhouse gases to trap energy, the planet entered a chilling feedback spiral. The surface cooled, which meant more ice, and more ice meant more reflected sunlight bouncing harmlessly back into space. Even when the sun's rays reached Earth, most of that light simply bounced off the white crust of the frozen oceans. The air above was thin and still, stripped of humidity. Clouds likely became rare, because the atmosphere was too cold to hold much water vapor. It wasn't just freezing. It was eerily dry, a desert made of ice. If you could stand on the surface during that time, and somehow stay alive, you'd see a sky that looked different from the one we know. The air would have been so clear that stars might have been visible even during the day, glittering faintly against a dim blue haze. The horizon would stretch wide and silent, with the sun barely strong enough to cast a shadow. Even sound would travel differently. Cold air dampens it, so everything would seem muted, as if the planet itself were holding its breath. The oceans below this icy shell were suffocating too. With so little carbon dioxide left in the air, much of it had been absorbed by seawater and locked into carbonate minerals. That chemical imbalance made the oceans more alkaline and less capable of supporting life near the surface. The lack of gas exchange between air and water turned the seas into still, heavy reservoirs sealed under meters of ice. Deep below, hydrothermal vents continued to belch minerals and gases, but up top, the world was silent and sealed away. The irony is that the atmosphere didn't just disappear. It was still there, but it had become nearly useless at its job. It's a bit like having a blanket made of lace. Technically, you're covered, but the cold still finds its way through. The sun's warmth was hitting the planet, but it was like trying to heat a house with the windows open. Every bit of energy simply radiated back out into space. And with that loss of heat came a transformation of the very air itself. Cold air is dense, so the atmosphere compressed closer to the ground. Winds weakened. Storms that once churned the skies slowed to a whisper. Even the familiar patterns of weather, the dance of high and low pressure, broke down. The atmosphere had stopped moving. It wasn't just a quiet world. It was a still one. The strangest part of this frozen era is that it wasn't uniform. The upper layers of the atmosphere may have actually stayed relatively warmer due to sunlight and thin traces of ozone, while the surface below froze solid. This created an inverted temperature structure, warmer air above colder ground, a system that effectively trapped cold air near the surface and made thawing even harder. Nature had built a cold trap, locking the planet in its icy state, and while the atmosphere had ghosted the planet thermally, it didn't abandon it chemically. In this frigid lull, subtle interactions were still taking place. Volcanic eruptions continued beneath the ice, slowly venting carbon dioxide back into the air over millions of years. But at this stage, the effect was imperceptible. Earth was in a stalemate. Frozen oceans below, a thin and fragile sky above, and the faint, relentless glow of sunlight doing nothing to help. It's fascinating to think that the very thing that keeps us alive today, the greenhouse effect, was so weakened that the planet nearly became uninhabitable. We tend to think of carbon dioxide as a villain in modern times, but during Snowball Earth, it was the missing hero. Without it, the atmosphere became transparent to warmth. The planet shivered in cosmic silence. And so, the once vibrant Earth drifted through space, wrapped not in warmth, but in frost. The air had turned from protector to spectator, watching as the oceans froze and the continents disappeared under glaciers. The atmosphere had ghosted the planet, leaving behind nothing but a pale, reflective world, a frozen sphere orbiting a sun that no longer felt close enough. But deep within this stillness, something was quietly building. The volcanoes below hadn't gone silent. They were preparing their comeback, and in time, the atmosphere that had betrayed the planet would be rebuilt from the very fires beneath the ice. Imagine standing at the edge of an ancient shoreline, staring out at what should have been a rolling, endless blue sea. Instead, you see a vast sheet of white glass, thick and still, gleaming like a mirror that stretches beyond the horizon. No waves, no foam, no sound of water, just the faint groan of ice expanding and cracking under its own weight. Beneath that solid shell, the oceans of Earth had fallen silent, entombed under kilometers of frozen crust. During Snowball Earth, the planet's oceans were not just chilly, they were nearly solid. Scientists estimate that the ice could have been anywhere from 1 to 3 kilometers thick in some regions. That's thicker than the tallest mountain in the eastern United States. The ocean, which had once been Earth's life support system, turned into a cold, suffocating tomb. The sunlight that used to dance through waves could no longer reach more than a few centimeters into the ice. Everything beneath it was plunged into an eternal twilight. It sounds like the end of the world, and for many forms of early marine life it probably was. But the story isn't all doom. The miracle is that life didn't vanish, it adapted. Somewhere in that frozen darkness, life found loopholes in extinction's contract. Let's start at the top. When seawater freezes, It doesn't turn perfectly solid like a clean ice cube. Salt gets pushed aside as crystals form, creating tiny pockets of super salty liquid trapped between ice crystals. These pockets are extreme environments, bitterly cold, oxygen poor, and loaded with salt. But they're not entirely dead. Microbes could have survived inside them, slowly metabolizing nutrients and clinging to existence in microscopic liquid havens. It's the biological equivalent of camping out in a freezer and refusing to leave. Then there were the volcanoes. Even during this global freeze, Earth's internal furnace never shut down. Along the mid-ocean ridges where tectonic plates pull apart, magma continued to well up from below. Around these cracks, hot mineral-rich water gushed into the icy seas, creating hydrothermal vents. Today, such vents host vibrant ecosystems, powered not by sunlight, but by chemistry. It's likely that during Snowball Earth, similar refuges existed, bubbles of warmth and nutrients beneath the ice where microbes thrived in complete darkness. These vent communities may have been the ultimate survivors, Earth's hidden tenants, living out the cold apocalypse in style. To them, the global freeze wasn't an extinction. It was just a long winter's nap. Some scientists believe these vent-dwelling microbes became the ancestors of many modern forms of life, proving that evolution doesn't need sunlight. It just needs persistence. But what about the rest of the ocean? Beneath that thick ice, conditions would have been strange and alien. The water was likely dense, still, and anoxic, depleted of oxygen. Without photosynthesis from surface algae, oxygen levels would have dropped dramatically, forcing any remaining life to switch to survival mode. Instead of breathing oxygen, microbes might have used sulfur, iron, or methane as their energy sources, relying on chemical trickery to get by. And yet, even in this darkness, the planet wasn't entirely quiet. Glacial movements above sent deep rumblings through the ocean crust. Ice sheets slowly crawled and fractured, grinding against continents and ocean basins. Occasionally, huge cracks would open, releasing trapped gases or momentarily exposing slivers of the liquid ocean beneath to the thin air above. These events may have created brief windows where life could exchange gases with the surface, fleeting, precious moments of contact with the outside world. The freezing process itself also reshaped the chemistry of the ocean. As ice formed, it concentrated salts and other chemicals into the remaining liquid water, creating hypersaline pockets, basically, briny puddles on a planetary scale. These were so salty they could resist freezing even at extreme cold. Microbes in these environments may have evolved special biochemistry to survive, developing anti-freeze-like proteins and membranes that wouldn't burst from ice crystals. In a way, Snowball Earth forced evolution into creativity mode, teaching life how to endure the impossible. If you could dive beneath the ice, ignoring the whole instant death thing, you might see something eerily beautiful. Shafts of pale blue light would filter weakly through the ice above, illuminating faint outlines of crystals and frozen stalactites hanging from the underside of the surface. Occasionally, plumes of dark mineral-rich water would rise from the vents below, swirling like ghostly smoke in the gloom. Tiny microbes might drift through the haze, glowing faintly with bioluminescence, a flickering galaxy of life hiding beneath the planet's frozen skin. What's fascinating is that this scenario doesn't just tell us about Earth, it gives us a blueprint for other worlds. Moons like Europa and Enceladus, with their icy shells and hidden oceans, may be living their own versions of Snowball Earth right now. The way life survived beneath our planet's ice could be the same way alien life hides beneath theirs. In a sense, Snowball Earth was a test run, a cosmic rehearsal for life's ability to thrive under ice, lightless and alone. As the freeze persisted for millions of years, the oceans stayed locked beneath their icy prisons. The world above was bright, white, and silent. The world below was dark, still, and alive in secret. There was no sound of waves, no scent of salt, no tides, just endless ice. But beneath that frozen surface, tiny ecosystems whispered the one truth that defines all of life. Survival isn't about comfort, it's about adaptation. When the thaw finally came much later, the oceans that re-emerged weren't the same as the ones that froze. They had been transformed, chemically, biologically, and spiritually, if a planet can be said to have a spirit. Those trapped seas had incubated endurance. The life that endured there didn't just survive. It learned how to persist when the planet itself turned hostile. So yes, the oceans once froze into something like solid glass. But beneath that glass, life was already sketching the blueprints for its next act. The planet may have seemed dead from above, but under the ice, evolution was quietly getting ready for the future, a frozen cradle of resilience waiting for the warmth to return. It's one of the most ironic fashion disasters in planetary history. Earth, once comfortably dressed in oceans of blue and continents of green and brown, decided to swap its look for an all-white ensemble and immediately regretted it. Because when you coat an entire planet in ice, you don't just change how it looks, you change how it behaves. This glacial makeover turned the world into a cosmic mirror, bouncing sunlight back into space so efficiently that almost no warmth stayed behind. This phenomenon has a name that sounds deceptively simple: albedo. It refers to how much light a surface reflects. A dark surface like an ocean absorbs most of the sunlight that hits it, warming the planet. But ice? Ice is the overachiever of reflection. It sends most of that sunlight right back where it came from. The more ice Earth wore, the higher its albedo climbed, and the less heat the planet retained. It was the climate equivalent of wrapping yourself in tin foil and wondering why you're still cold. In the early stages of the freeze, this feedback loop was subtle. More ice meant a little more reflection, a little more cooling. But as glaciers expanded, swallowing continents and creeping across oceans, the effect became runaway. Once the planet reached a certain threshold, scientists call it the albedo tipping point, the cooling accelerated like a snowball rolling downhill. There was no going back. Earth had entered a phase of self-reinforcing chill. From space, the planet must have looked dazzling, almost too bright to look at directly. The once blue world had turned into a gleaming sphere of white, glittering under the sunlight like a giant pearl. But beauty, in this case, was deadly. The sunlight that hit the planet had nowhere to go. It was reflected instead of absorbed. Global temperatures plunged, and the ice thickened even more. The very feature that made Earth look like a frozen jewel was the reason it stayed that way for millions of years. This shimmering catastrophe didn't just freeze the land and seas. It reshaped the atmosphere. With less heat being absorbed at the surface, air circulation weakened. Winds slowed, cloud formation dwindled, and weather systems practically shut down. The skies became eerily clear, not the pleasant, blue sky kind of clear, but the sterile kind that comes from a lifeless cold. The planet's wardrobe malfunction had turned the atmosphere into a still, fragile shell above an endless white desert. And this was no uniform coat. Ice behaves differently depending on where it forms. Near the poles, it piled up into massive, continent-sized sheets that crushed mountains and buried valleys. Near the equator, where sunlight should have kept things lively, the ice was thinner but still relentless, glistening and smooth, stretching across what had once been tropical seas. In some places, strange patterns may have formed, and ridges and frozen dunes carved by slow, grinding winds. The planet was covered in layers of texture: frost, snow, crystalline glaze, each scattering light in 1,000 directions. If you were somehow standing on this frozen earth, the world around you would feel alien. The horizon would shimmer like polished glass, light scattering off every surface. Shadows would barely exist. Instead, everything would glow faintly, as though the ground itself were illuminated. The air would be sharp and still. The silence would be immense. The only sounds would come from distant cracks, ice shifting, expanding, groaning under its own weight. Every now and then, an avalanche might thunder across the frozen plains, the sound echoing for miles in the thin air. This planetary whiteness also changed how energy moved through Earth's systems. Normally, sunlight warms the ground, which then radiates heat upward, driving convection currents in the atmosphere and ocean. But with the surface locked in ice, that energy exchange stopped. The oceans below were insulated by their icy ceiling, and the atmosphere above was left cold and dry. It was as if the planet's heartbeat had slowed to a crawl. Albedo, in a sense, was both villain and victim. It started as a natural defense mechanism, the planet reflecting sunlight to cool itself, but went into overdrive. It's a bit like trying to cool your soup by blowing on it and ending up freezing the whole pot solid. Once the reflective surface took over, there was no easy way to reverse it. Even when volcanic eruptions occasionally belched carbon dioxide into the air, the ice's reflectivity made sure that the extra warmth barely made a dent. The planet was stuck in its shiny white outfit, no matter how uncomfortable it got. Over millions of years, this reflective prison reshaped the planet's identity. Dust and debris from meteor impacts occasionally darkened patches of ice, but not enough to change the global balance. Every snowfall renewed the mirror finish. Every glacier that calved and spread across the ocean surface and added another layer to the planet's blinding disguise. The Earth was not just cold, it was stubbornly cold, refusing to absorb even the kindness of the sun. But while the surface world lay silent, the mirror effect above it was slowly building tension. Because as sunlight kept reflecting away, volcanic gases beneath the ice were accumulating. Carbon dioxide was rising again, molecule by molecule, trapped in the air like invisible insulation waiting to catch fire. The planet's wardrobe malfunction, spectacular as it was, couldn't last forever. Sooner or later, those reflective sequins would have to come off. For now, though, Earth remained the universe's most extravagant disco ball, sparkling, freezing, and utterly lifeless on the surface. It was a world so bright it blinded, so reflective it starved itself, so beautiful it was deadly. The planet had learned a cruel lesson about fashion. You can look stunning in white, but if you wear it too long, you just might freeze to death. If the Snowball Earth was the universe's longest deep freeze, volcanoes were the impatient chefs banging on the oven door saying, "All right, enough already." Because while the surface of the planet was locked under kilometers of ice, the molten heart beneath never stopped moving. The Earth's interior doesn't follow the weather forecast. It's a constant cauldron of magma, convection currents, and pressure, utterly indifferent to whatever's happening up top. And during this frozen age, that indifference saved the world. Under the thick ice, tectonic plates continued their slow, grinding waltz. Where they collided or pulled apart, volcanoes erupted with their usual flair. Plumes of molten rock, jets of ash, and enormous amounts of carbon dioxide. Normally, that gas would be absorbed by rain, oceans, and rocks in a grand cycle that balances the atmosphere. But during Snowball Earth, that balance was broken. There was no rain, no weathering, and no ocean waves to capture those volcanic emissions. Every molecule of carbon dioxide that escaped into the air stayed there, stacking up like invisible insulation around the planet. At first, this made little difference. The planet was still too reflective, too locked in ice. Each new puff of volcanic gas disappeared into a sky that couldn't hold heat. But the volcanoes were patient. They didn't stop, over thousands. Then millions of years, they kept pumping greenhouse gases into the air. Slowly, imperceptibly, the atmosphere began to thicken with carbon dioxide. It was the world's longest and quietest rescue operation, one eruption at a time. Imagine the scene beneath the ice. Volcanic eruptions bursting through the seafloor, plumes of molten rock glowing red in the blackness. The water around them would have been near freezing, yet around the vent, it boiled with heat and minerals. Gases bubbled upward, trapped beneath the ice like air under glass. Each eruption added another layer of carbon dioxide to the trapped atmosphere, creating a growing greenhouse effect that no amount of frost could fully resist. And it wasn't just the mid-ocean ridges doing the work. Continental volcanoes, those towering mountains of fire, also played their part, and even through kilometers of ice, some eruptions may have punched through the frozen shell, sending ash and steam bursting into the sky. The contrast would have been astonishing. Fountains of glowing lava exploding into a world of white silence. Each plume carried carbon dioxide, sulfur dioxide, and other gases into the air, subtly rewiring the planet's thermostat. This buildup of volcanic gas didn't melt the planet overnight. It was more like a slow cooker set to thaw. Over millions of years, the greenhouse gases accumulated until the balance tipped. The ice still reflected sunlight, but now, more and more heat was being trapped in the air. The atmosphere thickened, the cold grip loosened, and Earth began to sweat. Tiny patches of melting appeared at first. Thin puddles forming atop glaciers. small cracks of open water along coasts. Then, as the warming continued, those cracks spread, merging into rivers and lakes that ate away at the ice from above and below. Volcanoes had essentially outlasted the freeze. Their persistence was unmatched. The same forces that had once helped freeze the planet, continental shifts and weathering, were powerless under this new wave of greenhouse warming. Eventually, the carbon dioxide levels reached hundreds of times today's concentration. The air became dense and hazy, filled with heat-trapping gases. For the first time in tens of millions of years, sunlight began to matter again. You could think of it as the ultimate planetary comeback. The very same volcanic activity that had helped shape Snowball Earth's frozen continents now provided the key to escape. As the ice thinned, water vapor joined the mix, another powerful greenhouse gas. The warming accelerated, feeding on itself. The white surface of Earth began to retreat, revealing darker patches of land and ocean that absorbed more sunlight. Albedo dropped, temperatures soared, and within a geological blink, the deep freeze began to collapse. What followed would have been a spectacle of chaos. As glaciers melted, enormous floods surged across continents, carving new landscapes. Oceans rose, swallowing ancient shorelines. The atmosphere, supercharged with carbon dioxide, turned the world briefly into a steamy greenhouse. Rain returned for the first time in ages. Acidic rain, loaded with volcanic gases, pouring down on freshly exposed rock. Thunderstorms crackled across skies that hadn't seen lightning in millions of years. The planet, after a long coma, woke up violently. For life, this was both a crisis and an opportunity. The extreme heat and chemical-rich waters would have been stressful for surviving organisms, but they also brought nutrients and new habitats. The glaciers that ground continents to dust had released minerals into the oceans, feeding explosive blooms of microscopic life. In a cosmic twist of irony, the same volcanoes that had turned Earth into a sauna were also setting the stage for an evolutionary springtime. Volcanoes, in their unpredictable and destructive way, had played hero. They were the planet's pressure valves, the agents of change that refused to stop burning even when the world froze over. Without them, the atmosphere might never have regained its greenhouse balance. Earth would have stayed locked in ice forever, an abandoned snowball orbiting a distant sun. Instead, their fiery persistence transformed despair into possibility. It's a reminder that not all heroes wear capes. Some wear magma. Volcanoes don't get much credit, mostly because when they show up, they tend to ruin the day. But in this case, their relentless eruptions were acts of salvation. They rebuilt the atmosphere molecule by molecule until the ice couldn't hold. And as the white veil of Snowball Earth finally began to melt away, steam rose from the thawing seas, clouds returned to the sky, and the world's color came back. The planet that had nearly frozen to death was reborn, hot, wet, and alive again. All thanks to the stubborn, fiery breath of its volcanic heart. For tens of millions of years, the planet had been locked in silence. Ice ruled the continents, the seas were sealed under glass, and sunlight had been little more than decoration. But deep in the atmosphere, invisible change was brewing. Volcanoes had been exhaling carbon dioxide non-stop and the air had grown heavy with it. Eventually, the greenhouse blanket thickened enough to trap more heat than the ice could reflect. It started slowly, a whisper of warmth in an endless winter, but once this balance tipped, the thaw hit like an avalanche. Picture the first signs of melting. Tiny fissures appeared in the ice, where pressure and heat combined to carve veins of water through the frozen crust. Pools formed in the sunlight, glistening like mirrors scattered across the surface. As the atmosphere warmed, these melt ponds deepened and widened, linking together to form rivers that snaked across glaciers. For the first time in eons, liquid water flowed freely across the land. Each droplet was a herald of change, eating away at the world's icy armor. Once the melting began in earnest, it didn't creep, it cascaded. Ice has a dangerous secret. The more it melts, the faster it melts. The exposed patches of darker rock and ocean absorbed sunlight instead of reflecting it, accelerating the warming. Before long, vast regions of ice cracked and calved into the seas, sending tsunamis echoing across newly thawed waters. The planet's white shell fractured like glass under a blowtorch. If you could have stood on one of those thawing continents, it would have been a front-row seat to planetary chaos. Imagine walls of meltwater roaring down from mountains of ice, carving valleys and gouging out basins in their wake. Glacial floods, known as meltwater megafloods, may have swept across entire regions, carrying chunks of ice the size of city blocks and dumping them miles away. Rivers that had been frozen for millions of years suddenly roared back to life, wild and unstoppable. It was Earth's great undoing, a cataclysmic unfreezing that rewrote landscapes faster than erosion had ever managed before. And it wasn't just water that surged, it was atmosphere. As the warming intensified, oceans began releasing gases that had been trapped under the ice. Methane and carbon dioxide bubbled up, thickening the greenhouse effect even more. What had been a slow simmer turned into a full boil. The air grew dense and moist, packed with humidity and storm energy. The skies filled with heavy clouds, and for the first time since the freeze began, rain fell, hard, hot, and relentless. That rain was unlike any we know today. Falling through an atmosphere rich in carbon dioxide, it turned acidic, dissolving freshly exposed rock as it hit the ground. The runoff carried minerals into the oceans, altering their chemistry. This chemical soup of dissolved carbonates and nutrients created fertile waters for the microscopic life that had survived in the planet's dark corners. It was as though the great melt had not only flooded the world but fed it, jump-starting new cycles of growth and transformation. Meanwhile, the seas themselves were rising, fast. As glaciers collapsed, trillions of tons of meltwater poured into the oceans, raising sea levels by hundreds of meters. Low-lying land vanished beneath waves. Islands disappeared. Entire mountain ranges that had once stood proud under ice caps were reduced to peninsulas and cliffs. The outlines of continents blurred. Coastlines redrew themselves overnight on the geological calendar. And with the water came sediment. As ice sheets retreated, they released torrents of ground-up rock and mineral dust that had been trapped beneath them. Rivers carried this slurry into the oceans, creating murky, nutrient-rich layers that spread across the seafloor. The world's chemistry was in flux. Minerals interacted with carbon dioxide, forming massive deposits of carbonate rock, geological fingerprints of this epic thaw that scientists can still read today. The transition was violent but brief. In geological terms, the planet defrosted almost instantaneously. Temperatures may have risen by dozens of degrees in just a few thousand years, a blink compared to the tens of millions that the freeze had lasted. Earth swung from deep freeze to greenhouse, skipping spring altogether. It was as if someone had leaned on the cosmic thermostat too hard, overshooting comfortable and landing squarely on tropical sauna. The atmosphere thickened with moisture, creating dense fogs and torrential storms. Monsoon-like rains drenched the continents, feeding newly thawed rivers and lakes. Thunder boomed over valleys that hadn't heard a sound in ages. Lightning arced through skies swirling with ash and water vapor. Volcanoes that had worked tirelessly through the cold now stood silhouetted against fiery sunsets, steam rising from their flanks as meltwater poured into their craters. The frozen world was alive again, loud, chaotic, and vibrant. For the life that had survived the freeze, this was both deliverance and disorientation. Microbes that had endured under ice now faced warmth, light, and chemistry they hadn't seen in millions of years. But with the thaw came opportunity. Sunlight reached the oceans again, awakening photosynthetic organisms that had been trapped in darkness. Algae bloomed in vast, green swirls, pumping oxygen into the air and fueling new chains of life. Evolution, which had been crawling, began to sprint. The Great Melt wasn't just the end of an ice age. It was a planetary rebirth. The floods carved out the landscapes we'd one day walk upon. The rains recharged the chemistry of life. The chaos seeded balance. And all of it, every drop, every storm, every plume of steam, was the sound of a planet coming back to life after the longest winter in history. For a while, Earth must have looked like a fever dream. Boiling clouds, steaming seas, and rivers cutting through ancient Ice Valley. But beneath the chaos was renewal. The frozen world that had once seemed doomed was now awake, reshaping itself into something warmer, wetter, and ready for the next act in the story of life. From ice cube to steam bath, Earth had flipped its switch, and as the last glaciers melted into the ocean, the planet exhaled, for the first time in eons, the warm breath of a living world. When the last of the Snowball Earth glaciers retreated, the planet didn't just thaw, it inhaled. After tens of millions of years spent trapped beneath frozen silence, sunlight finally reached the oceans again, and life wasted no time throwing the most ambitious revival act in history. Microbes that had spent the Ice Age huddled in dark refuges near volcanic vents, or under thin cracks of ice suddenly found themselves bathed in light and warmth. They had energy again, open water again, and, most importantly, freedom again. The stage was set for one of evolution's biggest plot twists, the Great Oxygenation Renaissance. During the long freeze, photosynthetic organisms, tiny, hardy cyanobacteria, had been running on life support. Trapped under ice, they had few opportunities to photosynthesize, and oxygen production had nearly flatlined. But now, with vast oceans open to the sky, sunlight poured down without obstruction. The cyanobacteria got back to work like over-caffeinated artists after a long creative block. Using sunlight to split water molecules, they began pumping out oxygen in massive quantities, turning the planet's chemistry upside down. At first, this oxygen was like an uninvited guest at a party that didn't yet know how to handle it. The oceans were full of dissolved iron, built up during the frozen years when oxygen was scarce. When oxygen met that iron, they reacted spectacularly, forming rust. Literally. The red, iron-rich rocks we find in ancient strata today, called banded iron formations, are the fossilized record of that chemical drama. Whole oceans turned reddish-brown as oxygen rushed in, oxidizing everything in sight. It was a planetary rusting event on an epic scale. Once the iron was exhausted, oxygen began accumulating in the water and, eventually, in the air. The atmosphere transformed from a thin, carbon dioxide-heavy shell into something new, something breathable. For the first time in ages, the planet's sky became oxygen-rich enough to support larger, more complex life forms. The air itself became an evolutionary engine, pushing biology to innovate. But this wasn't an instant makeover. The transition was chaotic. Oxygen, while life-giving to us, was toxic to many of the anaerobic microbes that had ruled the pre-oxygen world. For them, this was a mass extinction event. The very gas that fueled the rise of complex life was poison to their simple metabolism. As the atmosphere filled with oxygen, these ancient survivors retreated into the oxygen-free corners of the world. Deep underground, in stagnant mud, or in oxygen-depleted pockets of the ocean. In a way, Earth traded one crisis for another, but this time it was a crisis that sparked creativity. For the organisms that adapted, oxygen opened new doors, literally, new chemical pathways. Oxygen allows cells to extract far more energy from food than fermentation ever could. It was like upgrading from a flickering campfire to a nuclear reactor. This energy surplus made complexity possible. Cells could afford to grow larger, develop internal compartments, and cooperate in ways they never could before. Multicellularity began to take hold, not in a single leap, but through countless small partnerships that snowballed into new forms of life. Oceans that had once been dull and lifeless now shimmered with green and blue mats of photosynthetic microbes. These living carpets pumped out oxygen continuously, altering not just chemistry, but climate. The ozone layer began to form high above, shielding the surface from ultraviolet radiation. For the first time, the world wasn't just habitable, it was hospitable. The planet was stabilizing itself into a home. And then came the real fireworks. The Ediacaran biota, the first large multicellular organisms in Earth's history. They emerged not long after Snowball Earth thawed, living proof that the oxygenation boom had rewritten evolution's rulebook. These strange, soft-bodied creatures, ranging from frond-like forms to blobby discs, drifted, crawled, and spread across the seabed. They were the ancestors of all future animal life, from worms to whales to, eventually, the weird bipedal storytellers that now ponder them. It's almost poetic. The Great Freeze, which seemed like the ultimate extinction event, was actually the prelude to life's expansion. The very processes that nearly wiped out biology, ice, starvation, and suffocating cold ended up purging the planet's chemistry, preparing it for a breath of oxygen and a burst of innovation. Earth, it seems, has a flair for drama. It doesn't just crash, it resets. The oxygen boom didn't just change biology, it reshaped the entire planet. The new air composition cooled the greenhouse effect, moderating the climate. The oceans, rich in oxygen and nutrients from glacial erosion, became breeding grounds for biodiversity. Continental shelves turned into living laboratories, where evolution experimented freely. Every cell, every organism, was running on a new kind of fuel, one that allowed for speed, complexity, and connection. You could say this was the moment life learned ambition. No longer limited to single-cell simplicity, organisms could now build, specialize, and diversify. Nerves, tissues, and muscles became possible. Predation, movement, and sensing the environment. All of it stemmed from the chemical spark of oxygen. It was Life 2.0, a world ready to evolve not just to survive, but to thrive. If Snowball Earth was the universe's harsh teacher, the oxygen boom was the graduation ceremony. From that point onward, Earth would never again be the same kind of world. It had shed its icy shell, reinvented its atmosphere, and set life on an irreversible trajectory toward complexity. And in the grandest twist of all, we owe our existence to that sequence of catastrophe and recovery. Every breath you take today carries the legacy of those ancient cyanobacteria, those pioneers who turned sunlight and water into air and opportunity. Without their post-freeze revival, there would be no forests, no animals, no humans staring at the stars wondering how it all began. The great oxygen boom wasn't just an after-party to Snowball Earth, it was the beginning of everything that came next. The planet thawed, the air filled with breath, and life, once microscopic and meek, took a deep inhale and decided to become magnificent. When the last shards of Snowball Earth's icy armor finally melted, the planet emerged a little wiser. It had stared into the abyss of its own extinction, and, against all odds, thawed its way back. But what came after was more than just recovery. It was refinement. The Earth, once a reckless experiment in climate extremes, seemed to learn the art of stability. Like someone who'd nearly burned down their kitchen trying to boil water, it finally figured out how to keep the flame steady. For millions of years after the Great Thaw, Earth's systems quietly recalibrated themselves. The intense greenhouse atmosphere that volcanoes had built during the freeze was still thick with carbon dioxide, and that made the planet swelter like a sauna. But nature, ever the problem solver, started inventing balance. Rainfall, newly abundant, began dissolving carbon dioxide from the air. That dissolved gas reacted with minerals in rocks, forming carbonates and locking the carbon safely away. It was the beginning of one of Earth's most elegant self-regulation systems, the long-term carbon cycle. It works like this. Volcanoes release carbon dioxide into the air, warming the planet. Warmer climates lead to more rain, which enhances weathering of rocks. The weathering process pulls carbon dioxide back out of the atmosphere, cooling things down again. It's a seesaw of chemistry and geology, with the planet as both participant and referee. During Snowball Earth, this balance had been thrown out the window. Now it was back, and functioning better than ever. The continents, freshly exposed after the ice retreated, played their part in this planetary reset. Glacial erosion had ground down vast swaths of rock, leaving behind fresh mineral surfaces rich in calcium and magnesium. These minerals were like chemical sponges, eager to react with atmospheric carbon dioxide. As rain washed over the continents, it triggered reactions that sequestered the greenhouse gas in stone. This steady drawdown of carbon dioxide cooled the climate just enough to prevent a runaway hothouse. For once, Earth found the sweet spot between too cold to breathe and too hot to exist. But balance isn't just chemical, it's also geological. Deep within the planet, tectonic plates continued their endless drift, recycling crust and regulating volcanism. When plates subducted under one another, carbon locked in rocks was carried back down into the mantle, only to reemerge through volcanic eruptions millions of years later. It was a planetary recycling program long before anyone coined the term. This rhythmic give and take between surface and interior helped stabilize atmospheric gases over time. Earth had found a geological heartbeat. The oceans, too, had a role in maintaining this new equilibrium. After the Great Thaw, they became the planet's carbon vaults, absorbing and releasing carbon dioxide in a slow, steady rhythm. Marine organisms began evolving ways to use carbon and calcium to build shells, inadvertently creating another carbon sink. When those organisms died, their shells sank to the seafloor, locking carbon away in sediments for eons. It was as if life itself joined the planetary effort to keep the climate from spinning out of control again. What's remarkable about this new system is how self-correcting it became. When temperatures rose, chemical weathering sped up, pulling carbon dioxide out of the atmosphere and cooling the planet. When temperatures dropped, weathering slowed, allowing volcanic carbon dioxide to build back up and warm things again. It wasn't perfect. It never is. But it kept the climate within a range where life could persist. The extremes of Snowball Earth had forged resilience into the planet's DNA. This newfound stability also allowed ecosystems to flourish in ways they never could before. With the climate no longer swinging between deep freeze and inferno, life had time to adapt, evolve, and diversify. The first complex marine ecosystems took hold, filling the oceans with creatures that filtered, crawled, and swam. Stability, it turns out, is a powerful catalyst for creativity. But perhaps the most profound change was invisible: the transformation of the atmosphere into something balanced and breathable. Oxygen levels rose and stabilized. Carbon dioxide found its long-term equilibrium. The sky turned from a greenhouse haze to the clear blue canopy we know today. Clouds returned as the planet's thermostat regulators, reflecting sunlight when things warmed too much and holding in heat when they cooled. Earth had, in essence, designed its own climate feedback system, a kind of planetary autopilot that kept conditions livable. Of course, this balance wasn't a conscious decision. Earth didn't sit down and say, "Let's never do that again." It was the inevitable outcome of physics, chemistry, and time, the planet's natural resilience finding its groove. But it's tempting to think of Snowball Earth as a cosmic lesson in humility. After almost freezing itself to death, the planet seemed to learn moderation. Extremes, it realized, are not sustainable. Balance keeps you alive. That balance would be tested again, of course. Ice ages would return, though never as total as before. Greenhouse intervals would come and go. But the feedback systems forged in the aftermath of Snowball Earth kept the climate from spiraling completely out of control again. Even mass extinctions and meteor impacts couldn't entirely derail the stability that emerged from that ancient catastrophe. If Earth were a person, this was its finding itself phase, a moment of self-awareness after a rough adolescence. It had learned how to regulate its own moods. It could sweat, but not overheat. Shiver, but not freeze solid. It had figured out how to keep the cosmic thermostat just right. And yet, as we look around today, it's clear that lesson was only half learned. By us, at least. Humanity has inherited a planet that mastered balance, and we've spent the last few centuries testing its limits. We've become the new volcanoes, pumping carbon dioxide into the air faster than nature can absorb it. The same mechanisms that saved the world once still exist, but they work slowly, on million-year timescales. Earth, patient as ever, will adjust eventually. It always does. But the real question is whether we, its restless tenants, can rediscover the same wisdom the planet earned through catastrophe. That moderation, in every form, is survival. After Snowball Earth, the planet didn't just thaw, it matured. It found rhythm, feedback, and resilience. And in that newfound steadiness, it became the world we call home. If you want to listen to Earth's oldest stories, you won't find them written in books. You'll find them pressed into stone. Fossils, minerals, and layers of rock are the planet's diary, etched over billions of years. And when scientists cracked open certain cliffs and canyon walls in places like Namibia, Australia, and the Canadian Arctic, they stumbled upon something extraordinary, a geological confession. The rocks were telling the tale of a time when the entire world froze solid and then melted in an explosive comeback. Let's start with the first clue, the glacial till. This is the geological signature of ice itself, a messy mix of crushed rock, gravel, and mud left behind as glaciers advance and retreat. Normally, you'd expect to find such deposits in high latitudes, near the poles, or up in mountains where modern glaciers still exist. But during the hunt for ancient clues, geologists discovered glacial till in the most unlikely places, rocks that had once formed near the equator. The only explanation was chillingly literal. The tropics had frozen solid. In Namibia, layers of reddish sandstone rest directly on top of a jumbled base of glacial debris. These rocks are more than 500 million years old, but they still carry the fingerprints of ice that scraped across them. You can see grooves, striations, etched into the surface, carved by glaciers dragging rocks along their base like cosmic sandpaper. To touch these rocks is to feel the scars of Snowball Earth itself. But the story doesn't end with ice. Just above those glacial layers, something strange appears, a layer of limestone rich in carbonate minerals. It's as if the planet went from deep freeze to tropical beach overnight. This sudden switch is known as a cap carbonate, and it's one of the most striking geological signatures on Earth. These layers formed when the Great Melt released enormous amounts of carbon dioxide into the atmosphere. The warming oceans became saturated with the gas, which then precipitated as minerals that settled out of the water, creating thick layers of carbonate rock. Imagine the scene: glaciers retreating, torrents of meltwater rushing into the seas, and oceans fizzing with chemical reactions like an over-carbonated soda. The chemistry of the planet flipped almost instantly. Where once there had been frozen silence, there were now roaring rivers, crashing waves, and the hissing sound of chemical transformation. The cap carbonates record that exact moment, the chaos of thawing Earth captured in stone. Scientists studying these formations describe them as geological whiplash. The rocks literally show the world switching from ice age to hothouse within a span of just a few thousand years, a blink in geological time. Beneath your feet, you can trace the transition, gritty glacial debris giving way to smooth tropical limestone. It's as though the Earth itself had flipped from Arctic to Caribbean in a single heartbeat. But the rocks whisper more than just temperature changes. They tell a story of survival. Within some of these post-glacial deposits, scientists have found microscopic fossils, stromatolites, microbial mats, and other simple life forms that re-emerged as the ice retreated. These fossils aren't glamorous, no dinosaur bones or trilobites yet, but they are profound. They're evidence that life didn't just endure Snowball Earth, it rebounded. After tens of millions of years entombed beneath ice, the biosphere reawakened, and these tiny survivors were the first to colonize the thawed world. In some places, the fossils even show signs of experimentation, new microbial structures and chemical signatures that hint at the beginnings of more complex ecosystems. It's as though the post-freeze world was a blank canvas, and life couldn't wait to paint again. The melting released a flood not only of water, but of nutrients, iron, phosphorus, and carbon, carried by glacial runoff into the seas. The result was a global bloom, a biological fireworks show visible only under a microscope, but with consequences that would shape the rest of evolution. And while the fossils tell of renewal, the rocks themselves tell of instability. Chemical analysis of ancient sediments reveals wild swings in carbon isotopes, tiny differences in atomic makeup that record how carbon cycled through the planet. These swings suggest that during and after the Great Melt, Earth systems were anything but calm. The atmosphere, oceans, and biosphere were in a planetary tug-of-war, trying to find a new equilibrium. In short, Earth was rebooting itself. In calm deposits, evidence of violent weathering appears. Minerals formed by acidic rain, eroded surfaces shaped by powerful floods, and layers of sediment piled up by torrents of water that would have dwarfed any modern river. The melt had unleashed chaos, and the land bore the marks. Each layer of rock, each grain of sand, is a timestamp of destruction and recovery. Even the color of the rocks tells a story. Deep red layers suggest oxidation, oxygen reacting with iron as the atmosphere grew richer after the thaw. It's a subtle but powerful signature of the planet's transformation. The very air was changing, and the rocks were recording every breath. Taken together, these clues, from the frozen striations at the base to the carbonate caps above, form a complete narrative arc. freeze, melt, and rebirth. They're not just stones. They're a geological symphony, every layer a note in the song of survival. When scientists first pieced together this evidence, it was revolutionary. Before these discoveries, the idea that Earth could freeze entirely was considered absurd. But the rocks didn't lie. From Namibia's desert cliffs to Canada's glacial mountains, from China's limestone beds to Australia's red plains, the planet's skin carried the same message. It had once been buried in ice, from pole to pole. Standing before one of those outcrops today, you can almost hear it, the faint whisper of ancient catastrophe. The stones tell you of a world that broke, mended, and reinvented itself. They speak of silence, then flood, then life. They remind us that the earth remembers everything, and that even after the deepest freeze, there's always the possibility of thaw. The Snowball Earth event was as close to planetary death as it gets. The oceans froze, the air thinned, sunlight vanished, and nearly every corner of the planet turned hostile. If life had simply given up, nobody would have blamed it. Yet, against all odds, life didn't surrender. It improvised. It hunkered down, rewired its chemistry, and dug into the few refuges left where conditions weren't quite apocalyptic. These microscopic survivors didn't just endure the cold, they outsmarted it. To imagine their tenacity, picture a world where the surface temperature hovers far below freezing, where sunlight barely filters through kilometers of ice, and where oxygen is nearly non-existent. In that world, the creatures that persisted weren't anything like us. They were single-celled pioneers, microscopic rebels that learned to thrive where everything else froze solid. They had one goal: survive until the next sunrise, even if that sunrise was 10 million years away. One of their most ingenious survival strategies came down to chemistry. When the oceans froze, they didn't freeze evenly. The salt in seawater forced ice crystals to exclude it, concentrating briny pockets of liquid within the ice. These salty microenvironments became tiny sanctuaries where liquid water, and therefore life, could persist. Within these microscopic salt chambers, bacteria and archaea carried on with their quiet business of metabolism, even as the rest of the world lay encased in ice. To cope with the bitter cold, many of these microbes evolved molecular antifreeze. Some produced proteins that kept ice crystals from forming inside their cells, tiny biological shields against the cold. Others slowed their metabolisms to a near stop, entering a state so close to suspended animation that they might as well have been frozen in time. When energy ran low, they switched gears, surviving on scraps of chemical energy released by the slow decay of organic matter trapped beneath the ice. But not all life stayed put. Beneath the frozen oceans, cracks in the Earth's crust opened into hydrothermal vents, fiery oases in a frozen world. These vents spewed hot, mineral-rich water, creating pockets of warmth and nutrients on the seafloor. Around these vents, life found a foothold. Microbes clustered there, feeding on sulfur and hydrogen instead of sunlight. They didn't need photosynthesis. They had chemosynthesis, a process that turns raw chemicals into energy. It was as if the Earth itself had built tiny furnaces in the dark just to keep life alive. Somewhere near volcanic regions, other microbial communities likely thrived in subglacial lakes heated from below. The combination of heat and pressure prevented these lakes from freezing solid, creating deep, hidden ecosystems that never saw the sun. Modern examples like Lake Vostok in Antarctica, sealed under 4 kilometers of ice, offer a glimpse of what those ancient refuges might have looked like. Even today, microbes in such lakes live entirely cut off from the surface, drawing energy from minerals and gases rather than light. This ability to survive on chemical energy turned out to be one of life's greatest evolutionary tricks. It meant that even when photosynthesis was impossible, biology could still tick along in the shadows. That versatility, life's refusal to specialize too narrowly, was what kept it alive through the snowball crisis. It's the reason life didn't just vanish when the world turned hostile. And while the big picture of Snowball Earth seems desolate, at the microscopic level, it might have been buzzing with quiet persistence. Within, cracks in the ice, in briny films beneath glaciers, and along seafloor vents, microbial colonies endured in staggering diversity. Each pocket of survival became an experiment in adaptation. Some microbes evolved thicker membranes. Others changed their enzymes to function in near-freezing temperatures. Over millions of years, those subtle changes stacked up into new abilities, biochemical tools that would later fuel evolution's next great leap. It's tempting to see these tiny survivors as passive victims of circumstance, but in truth, they were architects of the future. When the ice eventually melted, it was these microbes that reawakened first, flooding the newly thawed oceans with oxygen, nutrients, and genetic diversity. Their endurance ensured that life didn't just resume, it reinvented itself. They were the seed stock of evolution, waiting patiently for warmth. And they weren't just survivors of one disaster. They were teachers. Modern extremophiles, organisms that live in boiling hot springs, acidic lakes, and Antarctic ice, carry the same strategies honed during Snowball Earth. They're living fossils of survival, reminders that life's toughness isn't an accident but a legacy. Every bacterium that thrives in a salt crystal or a hydrothermal vent today is echoing the same persistence that carried the biosphere through its coldest chapter. When scientists study these extremophiles, they're not just peering into Earth's past, they're glimpsing possibilities beyond it. If microbes could survive the hellish freeze of Snowball Earth, they could just as easily endure the icy oceans of Jupiter's moon Europa or the frozen crust of Mars. The same chemistry that saved life here might very well sustain it elsewhere. Snowball Earth didn't just shape our planet's biology. It taught us that life, once born, is astonishingly hard to kill. Think about that for a moment. The reason you exist, the reason forests grow, birds fly, and humans argue about coffee is because microscopic ancestors once refused to give up. They clung to warmth in the dark, shared energy through chemical reactions, and waited for the light to return. Every living thing today is an echo of that defiance. So, the next time you see frost on a window or ice forming on a pond, imagine what it once meant to be alive in a world where ice stretched from pole to pole. Somewhere deep under that frozen shell, life whispered, "Not today." It hung on long enough to rewrite the story of the planet. Those ancient microbes didn't just survive, They carried the torch through the darkest winter in Earth's history, and when the world thawed, they emerged triumphant, ready to evolve into everything that followed. Coral reefs, redwoods, whales, and humans, all descendants of the creatures that refused to die. It sounds like science fiction, but it's a question that quietly haunts climate scientists. Could the planet hit the reset button again and plunge back into a Snowball Earth scenario? The short answer is not easily. The long answer is a little more complicated and far more fascinating. Because to understand whether Earth could ever freeze over again, we need to understand why it hasn't since the last time. The planet has spent hundreds of millions of years fine-tuning its thermostat, and the dial no longer turns quite as freely as it once did. Back in the Precambrian era, Earth's atmosphere and continents were still amateurs at climate control. Carbon dioxide came and went with reckless abandon. The continents weren't arranged in ways that evenly distributed heat, and the sun was dimmer than it is now. Those were the perfect ingredients for catastrophe, a delicate balance where just a small drop in greenhouse gases could trigger runaway freezing. Today, the situation is very different. The sun shines about 6% brighter, which may not sound like much, but it's enough to make global-scale glaciation far harder to achieve. Our planet, in essence, now runs warmer by default. That being said, it's not completely immune. In theory, if carbon dioxide levels in the atmosphere ever dropped dramatically again, say, through some colossal geological or biological event, the same vicious cycle of cooling and reflection could start over. The oceans would begin to freeze. Their bright surfaces would reflect sunlight, and the cooling would cascade. It's the same self-reinforcing feedback that froze the world before. The difference is that now it would take a far bigger push to get the ball rolling. One of the few things that could hypothetically trigger such a freeze would be a combination of extremely low greenhouse gas levels and an extended dip in solar radiation. Imagine a world where volcanic activity almost completely stopped, halting the flow of new carbon dioxide into the air, while rock weathering continued to pull carbon out. Over millions of years, that could theoretically strip enough greenhouse gases from the sky to tip the balance. Add in some big shifts in ocean circulation or continental drift, and you might just get a global chill. But before you start stocking up on space heaters, rest easy. Nature's not lining up those dominoes anytime soon. Modern Earth has built-in buffers that prevent such extremes. Volcanoes never truly sleep, and they constantly replenish carbon dioxide. The ocean atmosphere system now works like a thermostat, responding to changes with stabilizing feedbacks. Even the biosphere itself, plants, plankton, and soil microbes, acts as a climate moderator, absorbing and releasing carbon in a slow, steady rhythm. Earth has learned to self-correct, a trick it earned the hard way. And then there's the human factor. If Snowball Earth was a story of too little carbon dioxide, today's story is the opposite. Our industrial civilization is releasing greenhouse gases at rates that make volcanoes look modest. In just a few centuries, we've nudged the carbon dial upward more than nature would in hundreds of thousands of years. We've gone from worrying about freezing to worrying about frying. That irony isn't lost on scientists. The very gas that once saved the planet from its frozen prison is now the one threatening to overheat it. Carbon dioxide has always been Earth's climate throttle. Too little, and we freeze. Too much, and we roast. Right now, we're flooring the accelerator. In that sense, the idea of another global freeze feels almost comforting, until you realize it would take an apocalypse-level collapse of carbon emissions to make it happen. Still, imagining a future Snowball Earth isn't entirely pointless. It forces us to think about the fragility of planetary balance. Earth's climate system isn't a static machine. It's a living, breathing interplay between rock, air, and life. Every feedback loop has limits, and even the stabilizing systems that keep things comfortable could, in theory, falter under the right conditions. Suppose a catastrophic drop in volcanic activity coincided with a massive increase in rock weathering due to uplifted mountain ranges, say, a super Himalaya event. Over millions of years, that could slowly drain the atmosphere of carbon dioxide, one molecule at a time. It wouldn't happen fast enough for humans to notice, but it could reshape the climate for whatever life exists far in our future. There's another possibility: cosmic interference. The sun itself is far from a steady heat lamp. Over long time scales, it cycles through variations in brightness and activity. If a prolonged solar minimum overlapped with already low greenhouse gas levels, the result could be planetary-scale cooling. Even small reductions in sunlight can have outsized effects when combined with reflective ice and low atmospheric heat retention. But even then, Earth has an ace up its sleeve: geological persistence. As the planet cools, weathering slows down, allowing volcanic carbon dioxide to build up again. Eventually, that buildup would reverse the cooling. The system self-rights, though the process might take millions of years. It's nature's version of a very slow emergency brake. So, could it happen again? Theoretically, yes. Realistically, not for a very, very long time. Our planet's days of complete glaciation are probably behind it. The sun's gradual brightening over billions of years means that the next great climate extreme won't be ice, it'll be heat. Long after humans are gone, the oceans will one day begin to boil, not freeze, as the sun's growing intensity turns Earth from a blue planet into a barren one. Still, Snowball Earth remains an important cautionary tale. A reminder of how dramatically feedback loops can transform the planet. It tells us that climate is not guaranteed, and that some small changes can tip big systems into chaos. The difference now is that we are the ones turning the knobs. If the ancient world taught Earth that moderation is survival, perhaps it's trying to teach us the same lesson. The next Snowball Earth may never come, but the next climate tipping point could. The question isn't whether the planet can survive it. It always does. The question is whether we'll still be around to read the story it leaves behind in stone. When we picture cataclysms, we tend to think of endings, apocalypses that wipe the slate clean. But Snowball Earth was both ending and beginning. It was an extinction and a genesis, a planetary deep freeze that cleared the stage so something new could emerge. Before the ice came, Earth was a microbial world, a quiet ocean planet ruled by single-celled life that had changed little for billions of years. After the thaw, it was a crucible of complexity, a world ready to experiment, evolve, and diversify. What looked like a catastrophe was, in truth, evolution's greatest makeover. The freeze acted like a natural reset of the biosphere. During those tens of millions of frozen years, life didn't vanish. It went underground, quite literally. In isolated pockets beneath the ice, within hydrothermal vents, or in salty cracks of brine. Microbes evolved new ways to survive in extremes. These evolutionary experiments, honed in cold, dark environments, became the foundation for resilience. When the thaw came, the survivors didn't just repopulate the oceans, they reinvented life. The post-snowball world was a radically different planet. Glaciers had scoured the continents bare, grinding mountains into dust and flooding the oceans with minerals. Iron, phosphorus, and calcium poured into the seas, creating a banquet of nutrients that fueled explosive biological growth. This sudden chemical feast gave photosynthetic organisms, those tiny sunlight eaters, the resources they needed to multiply beyond anything the planet had ever seen. The oceans turned emerald with new life. Oxygen levels soared, and for the first time the air itself became a tool evolution could sculpt with. This oxygenation surge set off a chain reaction that transformed everything. With more oxygen available, cells could extract energy more efficiently. That allowed them to grow larger, specialize, and cooperate. It was this biochemical revolution that made complex multicellular life possible. In other words, Snowball Earth's cold grip was the unlikely prelude to the rise of animals. The very trauma of freezing and thawing pushed evolution to innovate. And what followed was nothing short of spectacular. Within a few tens of millions of years, the oceans teemed with bizarre, elegant organisms, the ancestors of nearly every modern creature. The Ediacaran biota appeared first, soft-bodied forms that looked like quilts and fronds, absorbing nutrients directly through their skin. They were unlike anything before or since. Biological art pieces from a world still experimenting with the concept of animal. These strange pioneers set the stage for the Cambrian explosion, when life truly went wild and diverse forms filled every ecological niche. Without the Great Freeze, evolution might never have gathered the energy, or the oxygen, to make that leap. But Snowball Earth's influence ran deeper than biology. It reshaped the entire planet's systems. The thick ice sheets had scraped continents raw, redistributing sediments and altering the flow of ocean currents. Those changes helped establish the modern circulation patterns that now move heat and nutrients around the globe. The glaciers, in a sense, had remodeled Earth's plumbing, ensuring that the post-freeze oceans were dynamic and alive. The atmosphere, too, was reborn. The massive carbon dioxide buildup that ended the Ice Age didn't just warm the planet, it permanently altered the balance of gases in the air. The interplay between carbon, oxygen, and nitrogen reached a new equilibrium, creating a climate stable enough to sustain complex ecosystems for hundreds of millions of years. Snowball Earth didn't just reset life, it reset the rules of habitability itself. It's a paradox that the coldest period in Earth's history may have created the conditions for its most vibrant age. Yet, in nature, destruction and creation often walk hand in hand. The freeze purged stagnation. It forced evolution to adapt, to innovate under pressure. and then to explode into diversity once the shackles melted away. Like a forest fire that clears old growth to make way for the new, Snowball Earth scorched the biosphere with ice, and from that desolation came renewal. And in a cosmic sense, this wasn't just luck. Catastrophes like Snowball Earth may be necessary ingredients for intelligent life. Too much stability, and evolution stagnates. Too much chaos, and life can't persist. The freeze was a brutal calibration, a test that life passed, and in doing so, became stronger. It's humbling to think that our existence traces back not just to warmth and sunlight, but to cold and endurance. Humanity's ancestors owe their spark to microbial survivors that outlasted a frozen apocalypse. The fingerprints of Snowball Earth still linger everywhere. The oxygen we breathe, the complex ecosystems that cradle us, the very resilience of life itself. All of it was forged in that frozen crucible. Even the geological record, with its stripes of red ironstone and pale carbonates, stands as a monument to that rebirth. Every rock whispering of ice and melt is a page from the story of how a nearly dead world taught itself to live again. If the universe writes stories, Snowball Earth was one of its finest plot twists. A planet freezes solid. Life huddles in the shadows. And then, when the thaw comes, the world bursts into color, sound, and complexity. It's a reminder that progress isn't always born from comfort. Sometimes, it takes catastrophe to unlock creativity. So, the next time you see a snowflake, remember, the same forces that shaped its delicate pattern once reshaped the entire planet. The great freeze that nearly ended life became the forge that built the future. Snowball Earth didn't destroy the story. It flipped the page. From that ancient ice, evolution stepped into the sunlight for the first time, and the long path toward coral reefs, birds, forests, and us began. The planet had been broken, frozen, and remade. And when the universe finally pressed defrost, life didn't just survive. It bloomed.